Implicit Logarithmic Differentiation. Hello everyone. Let's begin our lesson on implicit logarithmic differentiation. To start, let's recall what we have covered in our previous sections. Up until now, we have learned how to differentiate functions where y is explicitly defined in terms of x. A classic example of this would be a function such as y equals x to the power of x, where y is already isolated on one side of the equation. However, as we progress into more advanced mathematical problems, you will encounter equations where x and y are intertwined. In these scenarios, the variables are mixed together in a single equation in such a way that y cannot be easily isolated or expressed as a simple function of x. When we face these implicit equations, specifically those where variables appear in both the base and the exponent, we cannot use our standard methods. Instead, we must employ a specialized approach known as implicit logarithmic differentiation. In the upcoming slides, I will guide you through the challenges of this method and provide a clear step-by-step methodology to solve these complex problems. Understanding the challenge. Now that we have introduced the concept of implicit logarithmic differentiation, let's look at why this process requires a specific approach. Consider an equation such as x to the power of y plus y to the power of x equals a to the power of b. When students first encounter an expression like this, a very common mistake is to attempt to take the natural logarithm of both sides of the equation immediately. However, we must be extremely careful here. There is a common misconception that the logarithm of a plus b is equal to the logarithm of a plus the logarithm of b, but this property is mathematically incorrect. It is important to remember that logarithms only distribute over multiplication and division. They do not distribute over addition. Because we cannot take the logarithm of the entire sum on the left side, we cannot apply the standard logarithmic rules to the equation as a whole. Therefore, we must decompose the equation into smaller, more manageable parts before we can proceed with the differentiation. This brings us to the formal step-by-step methodology, which we will explore in the next slide. The step-by-step methodology. Now that we understand why we cannot simply take the logarithm of both sides when addition is involved, let us look at the formal step-by-step methodology to handle these types of problems. To differentiate an implicit equation where both the base and the exponent are variables, we follow these 4 specific steps. First, we begin with step 1, decomposition or substitution. Since we cannot apply logarithms to a sum, we simplify the equation by assigning a new variable to each term that has a variable base and a variable exponent. For instance, if we are working with the equation x to the power of y plus y to the power of x equals a to the power of b, we can let u equal x to the power of y, and v equal y to the power of x. By doing this, our complex original equation is transformed into a much simpler linear form. U plus v equals a to the power of b. Next, we move to step 2, individual logarithmic differentiation. Here, we treat each of our substituted variables, u and v, as separate entities. We apply the logarithmic differentiation technique to each one individually. This involves 3 substeps. First, take the natural log of the term. Second, differentiate that expression implicitly with respect to x. And third, solve for the derivative of u with respect to x or the derivative of v with respect to x, expressing the result in terms of x, y, and the derivative of y with respect to x. Once we have those individual derivatives, we proceed to step 3, summation of derivatives. We now go back to our simplified equation from the first step and differentiate the entire equation with respect to x. It is important to remember that since a to the power of b consists of constants, its derivative is simply 0. Therefore, the derivative with respect to x of the quantity u plus v equals the derivative with respect to x of a to the power of b, which implies that the derivative of u with respect to x plus the derivative of v with respect to x equals 0. Finally, we reach step 4, algebraic isolation. In this last stage, we take the expressions for the derivatives we found in step 2 and substitute them into the equation we created in step 3. From there, it becomes a matter of algebraic rearrangement. We group all the terms containing the derivative of y with respect to x on one side and move everything else to the other, allowing us to isolate the derivative of y with respect to x. In the next slide, we will put this entire 4-step process into practice with a detailed example to see exactly how these calculations unfold. Detailed example. Now that we have established the theoretical framework and the step-by-step methodology, let us apply these concepts to a detailed example. We are tasked with finding the derivative of y with respect to x for the equation x to the power of y plus y to the power of x equals a to the power of b, where a and b are constants. Starting with step 1, substitution. As we discussed in the previous slides, we cannot take the logarithm of a sum. Therefore, we decompose the equation by assigning new variables to the complex terms. Let u equal x to the power of y and v equal y to the power of x. This simplifies our original equation to u plus v equals a to the power of b. Now, we move to step 2, where we differentiate u and v individually using logarithmic differentiation. First, let's look at u equals x to the power of y by taking the natural log of both sides. We get the log of u equals y times the log of x when we differentiate both sides with respect to x. The left side becomes 1 over u times du dx. On the right side, we apply the product rule, resulting in di dx times the log of x plus y over x to isolate du dx. We multiply the entire expression by u substituting x to the power of y back in for u. We find that du dx equals x to the power of y times the quantity di dx times the log of x plus y over x. Next, we perform the same process for v equals y to the power of x taking the log, gives us the log of v equals x times the log of y, differentiating both sides with respect to x. The left side becomes 1 over v times dv dx. On the right side, the derivative is the log of y plus x over y times di dx. Again, we multiply by v to isolate the derivative, which gives us dv dx equals y to the power of x times the quantity log y plus x over y times di dx. We now proceed to step 3, combining the results. Since our substituted equation was u plus v equals a to the power of b, we differentiate the entire equation. Remember that since a to the power of b is a constant, its derivative is 0. Thus, we have du dx plus dv dx equals 0. By substituting the expressions we just derived for du dx and dv dx, we get x to the power of y times the quantity di dx times the log of x plus y over x, plus y to the power of x times the quantity log y plus x over y times di dx, equals 0. Finally, we reach step 4, solving for the derivative of y with respect to x first. We expand the brackets to separate the terms. This gives us x to the power of y times log x times di dx, plus x to the power of y times y over x, plus y to the power of x times log y, plus y to the power of x times x over y times di dx, equals 0. To isolate our target, we group all terms containing di dx on the left side and move the remaining terms to the right. This gives us di dx times the quantity x to the power of y times log x plus y to the power of x times x over y, equals negative the quantity x to the power of y times y over x plus y to the power of x times log y. To simplify the final expression, we can rewrite the terms using exponent laws. For instance, x to the power of y times y over x simplifies to y times x to the power of y minus 1, and y to the power of x times x over y simplifies to x times y to the power of x minus 1. Dividing both sides to isolate the derivative, we arrive at our final answer. Di dx equals negative the quantity y times x to the power of y minus 1 plus y to the power of x times log y, all divided by the quantity x to the power of y times log x plus x times y to the power of x minus 1. Common mistakes to avoid. Now that we have walked through a detailed example, let us discuss some common pitfalls. It is very important to be aware of these mistakes to ensure your calculations remain accurate. First, let's address the logarithm sum error. As we highlighted at the beginning of this lesson, you must never apply the natural logarithm to both sides of an equation if that equation contains addition. For instance, taking the log of x to the power of y plus y to the power of x is a mathematical error because logarithms do not distribute over addition. This is precisely why we use the substitution method we practiced in the previous slides. Second, be careful not to forget the chain rule. This is a frequent mistake in implicit differentiation. When you are differentiating the log of y with respect to x, remember that the result is not simply 1 over y because y is a function of x. You must multiply by the derivative of y, resulting in 1 over y times di over dx. Third, pay close attention to the constant derivative. In the example we just solved, we encountered the term a to the power of b. Since both a and b are constants, the derivative of a to the power of b is 0. Be careful not to treat this as a variable function. Constants always vanish during differentiation. Finally, avoid substitution neglect. When we substitute a term like u equals x to the power of y, we often start by differentiating the log of u. However, a common mistake is forgetting to multiply that result by u to isolate the derivative of u with respect to x. Always ensure you complete this algebraic step before plugging your results back into the main equation. Keep these points in mind as we move to our final summary. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of this process. First, remember that we use implicit logarithmic differentiation, specifically in cases where both x and y appear in both the base and the exponent, and the equation is structured such that y cannot be easily isolated on one side. As we highlighted when discussing common pitfalls, the biggest challenge is that logarithms do not distribute over addition. Therefore, substitution is our primary tool. It allows us to bypass the inability to take the logarithm of a sum by breaking the equation into smaller, manageable parts. If you look back at the methodology and the detailed example we just worked through, you will see that the process follows a very logical flow. We begin by substituting new variables, we differentiate those variables individually, we sum those results together, and finally, we isolate the derivative of y with respect to x. Ultimately, the beauty of this method is that it effectively transforms a complex exponential problem, which would otherwise be nearly impossible to solve, into a straightforward linear algebraic problem that we can solve through simple rearrangement.